Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have digital archaeology, trying to find where disk turbo loader code originated from. So you might remember from the Armalyte and from the Power Drift videos that I encountered this disk turbo loader and noted the similarities between the almost 2 years later released Power Drift compared to the Armalyte code. Here the disassembly is showing the Power Drift code, I think it was, compared to the Armalyte code on the right hand side, and the code differences were incredibly striking. The code similarities, were incredibly striking. The code on the Commodore 64 was practically identical to the code used in Armalyte. And then when I looked at the technical differences in more detail, I could see that the tables had this structure of having 8 bytes difference offset between each table as the serial bus was used as a lookup. Either it was using the X register or the Y register, doesn't really matter, to be honest. What's important is the structure or the intent behind the code. So I got to thinking, how many other files used similar Commodore 64 turbo loading code, and also how many files, disk files, games use similar 1541 side code. So I decided to use my automation framework connecting to the Vice debugger so that it would, in sequence, load each disk image, the original G64 disk image from original releases. It would load each of those into Vice. It would then wait for a write to 2000 in hex, and then it would wait for a sequence of writes anywhere within the 2000 to 8000 hex memory range. It would then scan for the interesting C64 and 1541 code signatures in memory using regex queries, and then it would also take screenshots and dump files and then store that data. Now, this scenario outline details, that was a high-level overview, but this scenario outline contains some of the more low-level steps that were needed to execute this automated code scan. This is using the BDD 6502 framework that I've been working on to help me debug my Commodore 64 code and also my hardware projects code, because they both use a 6502 processor. This is the regular expression that's being used to match the Commodore 64 side of code, and then there is a regular expression at line 32 which matches the 1541 expected code. This test was originally scanning over 1,000 G64 disk images. I was able to narrow it down somewhat with the first pass of executing the test. So a lot of the lines that you can see in the examples table down below are commented out. So it only really looks at the G64 images that I'm interested in. It's looking for this kind of code signature on the Commodore 64 side, so you can see that it's doing that 2-bit transfer with that memory table interleaving, lookup table interleaving. And then this pattern for the code in the 1541 is also interesting. So to have a positive match to try and find the earliest games that used this, I wanted to match the Commodore 64 side and the 1541 code side, because both together really would indicate in terms of code structure that it's using the same or at least very similar code. So I put these two detections into 2 different matched files. I scan these file names, but these ones that are commented out, they're not scanned anymore because those have already been pruned from the code scanning. Their disk loader doesn't seem to bear any or much resemblance to the disk loader that I'm interested in finding more about. So when it executes, it puts a whole bunch of debug files into the temp directory like this, the target temp directory within the C64 find code. Now I'm going to be releasing this source code for the C64 Find Code project, so you can see how it runs itself. But basically it runs Vice. It connects to the remote debugger in Vice and then issues commands, and then depending on the information it gets back from Vice, it executes more commands. So that's how it's able to take screenshots, it's able to take dump files, it's able to tell me when a specific code signature has been matched, either on the C64 or the 1541 side. Here I'm just validating that Armalyte has been detected, and that these ones here, this should be the next file along, this should be Power Drift, right? So it just basically tells me that the test is working acceptably, that it's able to detect the relevant code. So I'm going to let that run for a while in the background. Now these steps here, these are higher level steps, but these higher level steps contain lower level steps which do a lot of the behind the scenes work. So it sets monitor reply timeout thresholds, for example. It connects to the remote monitor on a TCP port. It sends the command watch store 2000 at hex, so on and so forth. It then steps through a number of hits. It then sets and it does a screenshot. It does another watch for a store range. It does another screenshot. It switches to the C64. It takes a register dump. It takes it gives a reply. It stores the reply of the register dump in a file, so I can look at that later on to see where it was executing at the time that it triggered the breakpoint, and so on and so forth. We can see here that from the small little screenshot, sorry, that in the icon there we could see that it was running Morpheus. So in the first pass of running this automated code scanning, Morpheus was one of the games that was using this. Now I jumped ahead here, but it's using 125 games so far to scan with. Most of these games range from 1988 to 1985. I'm trying to find the earliest instance of this turbo loading code. I also noticed that there were differences between the code, which we'll get into a little bit later on. So we can see here that the tests all passed correctly from the green execution, highlighting all of those step lines. We can get rid of that for now. So we can see from an initial view that actually lots of different games, probably around about 100 or so, I think, have a positive match for Commodore 64 side code and also the code running in the 1541 disk drive. This being the criteria for a successful match, it means that actually quite a high number of games reused this code. So if I have a look at, say for example, What is Eagles from 1985 by Hewson. I'm not entirely sure that the release date is entirely correct, but we can see here that it's actually kind of failed to run, and I can see already that there's a 1987 in there, so I don't think the release date in the preservation disk archive is entirely correct of 1985. I think it's 1987 because the game itself seems to say 1987, but the game kind of like seems to have crashed, or at least not successfully loaded because it's got that garbled data on the screen. A lot of it seems to be shifted character set, so it seems to be either VIC screen codes or PETSCII codes, or vice versa. So I'm just going to load that disk image manually in Vice to see exactly what it's doing. Oh, maybe the breakpoint just triggered quite... Oh no, there we go. So it's failed. So it failed to load, or at least start the game by the looks of that. So it says 1985, which is not entirely true because I can see 1987 there in the screen grab. So Protection by Graeme Ashton, May 1987. Now this earliest game, or relatively early game, even if it was in 1987, had a full name there, which really gave me a good hint. Graeme Ashton corresponds to GMA 87. These initials in memory are very interesting to me because it tells me that Graeme is obviously credited for doing the protection. Now, in the early days, especially people doing protection work would also be very skilled in writing disk turbo loaders, of course, because they're doing quite low-level disk stuff. So I was thinking at this point that perhaps Graeme would have done the work on the turbo loader as well for this game, and if this game was, from 1987, maybe there's earlier ones, and there are earlier ones because I can see that there are other candidates for matched 1541 and C64 side code in this game. For example, this game is Xevious, or Xevious, or whatever it is, Xevious, from US Gold, and I'm pretty sure that that one is probably dated correctly. Hopefully, you would hope so, right? And this game actually seems to run okay. So the automation catches the loading a quarter of the way up through memory, if you like. So this was copyright 1982 Namco, the original arcade game, but the C64 release was 86 apparently. So let's run it again. There isn't anything on the screen per se, apart from a whole bunch of data or code. This is the C64 side, and I can see by looking for DD00, which is the serial port updates, I can see quite clearly that this is the variant which uses... That's Bionic Commander. Not interested in that one right now. That was from a previous debugging effort. There you go, 121. I can see that it's using the 0-page A5 method, and the 0-page A5 method is also used by the Armalyte loader, if I remember correctly. There we go. Armalyte pre-calculates into A5, and then it uses A4 and A5 as pre-calculated 0-page addresses, or registers, if you like. I mean, 0-page is, the lower 0-page is actually really quick. It's almost like an extra extended register set for the 6502. I mean, it still stores in memory, but the 6502 accesses them really quite quickly. That's why sometimes 6502 programmers treat them as extended registers, because they are almost as quick as the registers themselves, but not quite. There's like a 1 or 2 cycles difference, depending on your addressing mode, of course. So that this code uses 0-page for the pre-calculated DD00 values, so you can see that it does a load with $A5, blah blah blah. But we could see that it's using the Y register to load DD00 at address 41F, sorry, for example, and it's got that table which also has the 8-byte offsets using the indexed value from the serial port. Here I've just noticed that there was a disassembly error, and actually the disassembly should have looked like this rather than trying to pick up the previous opcode, which was not really an opcode. It looks like it was a piece of data. So looking at this, it matches. Anyway, we have a load A with A4, blah blah blah. The load A with A5, the index with Y this time, so we can see that the code is practically identical on the C64 side of things. So Armalyte seems to have been using some code which is almost practically identical to the code in that release from years earlier. So this has got me really interested that somehow Armalyte and also somehow Power Drift is using this code. You can see if I put them side by side at the same memory address and then flip between them that they are practically identical. The parts of the code, excuse me, the parts of the code that we're interested in are practically identical. So looking at the 1541 side code, comparing it to Armalyte, we can see that actually the memory addresses are identical as well on the 1541 side. So my hypothesis to explain this observation is that the 1541 side of the code would tend not to be repositioned because it does not have to cooperate with any game code. All it needs to do is sit up in the drive's memory. It would normally be sent to the drive as a binary blob of data, so the person who's using or reusing this code would not tend to reassemble this code, or they wouldn't tend to move it around. They don't need to. The C64 side of code, however, is a lot different, of course. So the C64 side of code being having to cooperate with other game code that's loaded, etc., would tend to need to be modified to fit within the constraints of the game code. So if the original code was running in somewhere in memory, it might get altered to not be. So anyway, Xevious was released in 1986, so at least we can see that Armalyte, that was released in 1988, is using disk turbo loader code from 1986, which is really quite interesting. I'm just extracting the G64 because the version of Vice with ICU doesn't seem to want to run the release from the zip file, and to be honest, it's not running that well in Vice either. So that was a Vice for ICU anyway. It wasn't yet. No, doesn't seem to be working terribly well. We can see that it's screwing up quite horribly. It's filling the memory with garbage and then stopping. So yeah, no, that's not going to work. That's okay. We have plenty of tools that we can use to investigate this. So the Commodore 64 would sometimes has different screen or border color update algorithms, for example. So the color patterns will be different. The closeness, or the frequency, if you like, of the color changes will be changed. There was this file, this game, that had code use. So the 1541 and the C64 side of things matched with the code signatures that I'm looking for. Trailblazer was another one, and it has again a different border color change, look and feel to it. Superstar Ping Pong, again that kind of look and feel to it. What surprises me about this is how many games use very similar code. We can see again GMA 86, again PBJ GMA. Well, we know GMA is Graeme Ashton, right? Because that was a name that fitted from the screenshot. Sanctioned by Thalamus in 1986. This was also a game that I bought, I think, a long time ago. We can see this one is unusual. It's actually doing a pre-calculation into a non-zero page address. It's doing it into an absolute address, which is a 422 in hex this time, or 0422 in hex. This actually subtly changes the timing of the Commodore 64 side of code to the drive. I wonder if they realised that when they were tweaking this code. But the main portion of the code here is identical. The DD00 indirect indexed loads from the lookup table in stack space 0100 0108 0110 in hex 0118. They are all offsets into a lookup table into the stack space, and they are all offsetted by 8 bytes for each bit pair. This tends to indicate to me that the Commodore 64 side of code is practically identical to the code in Armalyte. Again, that was sanctioned, wasn't it? And that was 1986. If I look for the signature in the drive code, now the 1541 cannot find 1800, Now, this is intriguing. Maybe the Commodore 64 hasn't uploaded the code yet, because I can clearly see that there is some drive code in the Commodore 64's memory. Now, the current test, if you remember, just dumps the drive memory and it does a disassembly of the drive memory. It doesn't look in the C64's memory for drive code itself, but I can clearly see that the drive code is there. And I can clearly see that the drive code is practically identical. The memory address offsets are different, but that's because we're disassembling drive code inside the C64's memory, that it's basically storing it as a binary blob of data. So the test could actually do the automation, the code scanning test could actually be updated to look for drive code that hasn't been sent yet, that is sitting inside the C64's memory. This will hopefully find more matching instances of games by matching the 1541 code with the C64 side of things, because, well, as long as the drive code sitting inside the C64's memory is not encrypted, or scrambled rather. But basically, if I do a side-by-side comparison, you can see that they are practically identical. Again, with the Armalyte code compared to the, I think it was sanction code of the drive code in the C64's memory as a binary blob of data. So yeah, I need to improve the automated code scanning test to look for these cases. So let's run the web-based editor. So updating the test case. So we can see that those initials GMA 85, 86, 87, 88 in this case correspond to a protection scheme. We kind of know that already because the Graeme Ashton that goes along with those initials, GMA, and it's mentioned here, did the protection scheme. That's what he was credited as, and it's Securispeed, or Securispeed. That website was the C64 games preservation or disk preservation website where they discuss different disk protection schemes. We can see again the offset with 8 lookup table for decoding 2 bits at a time from the serial register. We can see the drive code sitting inside C64's memory, again using the ASL and store TXA and store ASL and store loadx, not store X, very, very similar code there. So I can see that there is a definite need to improve the test case to match that extra variant of code in terms of drive code sitting in C64's memory, because it hasn't been sent yet. And there we go. Line 23, I updated to scan the C64's memory, not the 1541 memory. So that was a typo in the previous test run execution. So I'm running the test run again now. So some of the test data is being recreated from the test run, of course. So here I can see now that test 107, T107 basically, test 107, is matching 1541 in C64 memory. I can see that 1541 in C64, indicating that that's how it has detected the 1541 code. It's already sitting in C64's memory. It just hasn't been sent to the 1541 yet. Or, alternatively, it has been already sent, the load has progressed to a certain extent, and the code is no longer sitting inside the 1541. But usually it would be because the C64 hasn't sent it to the 1541 yet. We can see why. It's because on some of these instances like this, there is a prompt if you want to use the fast loader or not. If you say no, it won't even put the fast loader in memory, for example. So in this case, the 1541 code would be detected in the C64's memory as long as it was in plain, as long as it wasn't scrambled or anything else like that, or compressed. Again, this game, whatever it is, says, do you want to use the fast loader? Some of the game releases say, do you want to use the fast loader? It will only work on perfectly aligned drives. Which is kind of true, although actually the fast loader is really well coded and it does cope, really quite well with variations in disk speed. Because it does that handshake, say, where the Commodore 64 says, I'm ready to receive, the drive says, I'm ready to send, the Commodore 64 says, okay, do send then, and then the drive comes back and then sends the data. So it does that two-way handshake. So it confirms that it's really actually ready. So actually it's not that variable in terms of performance, and actually you can have the screen on the Commodore 64 by doing a bad line check. So actually the code is really quite robust. It wouldn't be affected by drive speed. What would be affected by drive speed probably is the protection check, which is entirely different. Different code for the protection check compared to the turbo loader. Although both pieces of code may be resident in the 1541's memory at the same time. Maybe, possibly. We'll see. Sometimes they are, sometimes they aren't. Sometimes it's a two-step process, sometimes it's like a one-step process. Sometimes the protection check can be entirely different code to the main game code, which does all of the loading and everything else like that. Like in Armalyte, for example, the protection check I think in Armalyte was entirely different code to the turbo loader. The turbo loader, as we could see, was by, as we assume, by Graeme Ashton. At this particular point in time, the evidence is definitely pointing towards Graeme Ashton doing the disk turbo loader as well as the protection in those early releases. So I think, we can safely say, I think, pretty much for sure. But we'll check that later on. That's going to be fun. We can see here the initials. Again, GMA was here. GMA, do you want to use the turbo loader, blah blah blah. We can see the initialization, whatever it is, command, the disk command being sent from the Commodore 64 to the drive. We can see on the drive side, we've got, GMA 1980 something, right? I didn't quite see that as it was flashing on. So, thankfully, GMA put their initials, Graeme put his initials, all over the place. So it actually makes it a little bit easier to track down the assumed author or origins of this code. Again, very familiar code, right? The shifts, the store. The shifts, the ands, the store, the transfers from X or Y register. That's why we have in the regular expression a test for an X register or a Y register being used in the TXA or TYA instructions. So we have these code variants being automatically checked for in the regular expression. We can see that this early release from 1985 is Revs, and Revs seems to use this code as well, I think. So all very cool. It's one of the earliest releases, I think. So I've updated the test again now to specifically scan for the code variants to indicate during the test whether or not it has successfully matched either the 64 or 1541 site. If the C64 and the 1541 code is found in memory somewhere, then it writes to the file matching report. I only want those games where the C64 and the 1541 code identically matches. So here we go. Let's run that, see what we get. So this is the block of code that I'm looking for on the Commodore 64 side of things. As you can see here from the text file, and I'll commit this text file into source control as well, we can see that there are some variants that check for the screen raster position because the screen is on, so it checks for bad lines. So I'm checking for parts of the C64 code which are common across the major code variants, or as common as I can get them. we have 124 individual reports. Some of them don't match, and I'm going to further investigate those a little bit later on. The drive side of the code tends to be quite a bit different in terms of its bit shifting strategy. So I'm not entirely convinced that it's written by the same person, or it has been changed quite significantly. I'm not entirely sure. So the C64 side of the code, you'll see down here, look at CEC8, that the table lookup offsets are not 8 bytes, they're 1 byte, which indicates there is a different bit shifting strategy being used on the 1541 side of things. It tells me that although the C64 code matches, it doesn't really match. It matches the regular expression, but it doesn't match, I think, my criteria for whether or not the code is identical, because the table offsets are different. They're 1 byte rather than 8 bytes. Maybe some one-twiddled bits on the 1541 side. The wait for the bad line is also different as well. So this wait for bad line waits for a different number of vertical pixels on the screen compared to the bad line check that is being used for Armalyte, for example, or for Power Drift. So I'm not entirely convinced that this is exactly the same kind of code. The number of no-ops is the same. The stores are, I don't think, quite the same. See, OE is being used there. OF is being used there. So yeah, I'm not entirely convinced. And looking through this, the initial part seems to be roughly okay. But then the shifts and then, okay. So I think there's an initial serial port check up higher than that. Oh look, it's a disassembly error. Pretty sure it was a disassembly error, right? Did you see that? On the 1541 code. So at 04DE there should be an opcode 2C there. There seems to be 2 bytes of data. So CCAA, there seems to be at least 1 byte of data which is screwing up the disassembly. That should be 2C, not CC, but okay. You get the general gist of what it should be. It should be this bit 1800. Now with that change, the code comparison by visual inspection seems to be a lot more similar, right? So this version of the drive code is a subroutine, whereas the other version of the drive code is kind of like inlined slightly so that it does extra stuff. If we have a look for that piece of drive code, actually we can see that that piece of drive code exists at the same drive memory address as at least 38 other games, indicating that the drive code has not been changed significantly. However, that memory address used in the other game is not really used by the looks of it. Interesting. So that variant of the drive code is actually unusual in as far as I can ascertain so far by looking at different game files. So instead of the X register being used for the last 0F store, it's using the A register. Okay. This is the C64 side code. So the table bit offset is different. The byte offset, sorry, the byte offset in the table is different. So because the drive code seems to be a little bit prone to disassembly errors, because before, if it's a subroutine then sometimes there's data there, I'm going to stop checking for the initial bit. I'm going to just check for the following branch on plus instruction instead. because the BPL, the branch on plus instruction, seems to be more reliably disassembled compared to the unreliable disassembly of the first bit instruction, bit absolute, which is 2C in hex. I'm going to ignore that variant in the drive code of using accumulator or using X, but storing 0F in hex into the serial port of the drive, replying back to the C64 basically, or sending data to the C64. I don't look for it in the regular expression anyway, so I'm not going to have to update that variant of the code. But yeah, let's remove the first bit. Let's document this. So here, just documenting my decision rationale, if you like. So we now have 99 games which are positively identified by having practically identical C64 drive code. One execution, actually, of Vice killed the remote monitor TCP connection. Okay, I'm not entirely worried about that. That was only one test case or one test scenario out of all of them, so I'm just going to ignore that for now. It doesn't normally happen. So I can see now that there are more often correct identifications by the automation. There's 11 has a blank screen, very blank screen. Yeah, I think this is the one where Vice kind of like disconnected. We'll just, I think silently ignore that one for now. Oh, clearing memory pattern, look. Looks like some code was running then. It just got all the way to 2000 in hex. Ooh, okay. Yeah, it looks like, well, maybe the drive code just completely failed then. Or maybe the disk image is bad. Probably the disk image is bad, or maybe the emulation is not quite good enough. I'm leaning towards blaming the disk image at this particular point in time. Now this is the variant that I was talking about earlier on. Instead of doing TXA and store, shift and store, whatever it was, it just does a whole bunch of rolls and ASLs. So I'm a bit, not convinced about that one. Look, there's ASL 285 roll, ASL store, la 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 la. It does a whole bunch of. This is a much less optimal way of getting the bits from the drive to the C64. It's in the grand scheme of things, it's not that much slower, to be honest, because a lot of the time is taken still by the drive, loading data from the disk, decoding it, and then putting it inside its internal memory buffers for then sending to the Commodore 64. So actually it's not that much slower, really. But the code variant is such that, on the drive side of things, the code variant is such that I don't think it's by GMA, and I don't see GMA's initials anywhere in the memory. So at this point in time, I'm tending to lean towards the hypothesis that GMA did not write this variant of the code, and I don't see it that often. So I think we'll just put a pin in that variant of the loader code. I don't see here any hits. So yeah. So this file is going to go into source control, so you'll be able to see which games GMA's loader code was basically used in. And I was fortunate enough to be able to reach out to Graeme, and he replied, and he said yes, he confirms that the initials that you see are his and his friend, that he wrote the code, that there were revisions of the code over the years, and he still actually has the source code, as you can see there. And he sometimes used the name SecuriSpeed, and he actually owns the website SecuriSpeed with the intention of putting code up there on the website. So we know now that thanks to the automation, thanks to these reliable game disk image dumps in the G64 Disk Preservation Society website, that we now know that GMA code, Graeme's code, was used in probably at least 99 games, probably more, because I haven't looked in great detail the games between 88 and 1990, for example. I haven't looked at games later than that, and I haven't yet looked at games earlier than 1985, although, as we saw, there were only, 3 or 4 games from 1985 that used this kind of code. So I wasn't expecting to find anything in 1984, although I haven't quite done that yet, because I successfully reached a conclusion where I managed to reach out to Graeme and got that successful reply from Graeme giving some context. Actually, in one of the other messages, Graeme confirmed that he was using PDS 6502, the programmer's development system, which used back in those days an Apricot PC or something like that for code editing and assembling and then sending to the Commodore 64. It was a system used, as far as I remember, by Andrew Braybrook, who wrote Morpheus at the time he was using the PDS system. So yes, I think we'll leave that video there because we've reached a successful conclusion. Thank you very much for watching these technical deep dives into games, and also now a series on digital archaeology of disk turbo or fast loaders. Thank you very much for watching. Have a great day wherever you are.